So thank you. So can you hear me in the back? All right. So this whole workshop is on high-dimensional data analysis. And as you all know, inference gets harder very quickly in high dimensions. And just to give you a sense of how serious this problem is, I included some numbers here. So this example shows you the required sample size to ensure a certain mean square error in non-parametric density estimation. So in 1 dimension, you here need 4 observations. And in 10 dimensions, you already need more than 800,000. And in our case, we have data, we have observations that are often of the order of 1,000 or thousands of variables. So it's certain high dimensions, but it's not the super high dimensions that Theo Montag was talking about the other day. But fortunately, naturally occurring data often have a lot of redundancy. So there's low dimensional structure. And examples of structures include where you have groups or correlated variables. But this kind of sparsity may not be evident until you use a different basis representation. So in other words, you may need to do a transformation of your variables rather than selecting just a subset of the original covariates. And in yesterday's talk, Bosnaller showed the difference, how important that is for regression. Then you may also have structure that cannot be revealed by linear techniques. So you may have data that lie on a nonlinear structure. And we've seen empiric evidence for this for natural images. So if you now extract random patches from many, many images and then look at the distribution, you will see that much of the data will be concentrated along highly nonlinear submanifold in this higher dimensional space. And the reason is that small patches, they're dominated by geometries such as edges, and an edge has 2 natural degrees of freedom, translation and rotation. And that's natural constraints in the system. Then, so here are some more examples of structure in data. So on the top here, we see a microscopic cross-section of skin tissue. And at each pixel position, I've recorded the spectral characteristics. Here we see some examples of spectra for different tissue types. And you can see structure in the sense that if you look at adjacent bands, they're often correlated. Adjacent wavelength bands in the same spectra. And also if you move along the different layers in the skin tissue, you also see a gradual continuous change in the spectra because of a change in the chemical structure or a change in the thickness of the sample. Then you also have data such as words and genes where there's no reason to believe that there's any manifolds because variations are not continuous. But there are other types of structure. So this is an example from genetics. So here, each row represents an experiment, and we see the expression profile across different genes. Now, typically, these variables, they can occur in any order, but in this case, we've reorganized the experiments and the genes just to show you this type of grouping structure. And the grouping structure is often rather complex, and it also can occur on many different scales, which is one reason why hierarchical cluster schemes have been very popular in describing or exploring these kind of sets. So question here is, can you find features that reflect this inherent organization? So as I see it, there are two main issues in high-D data analysis, and they've been mentioned in the previous talks, but perhaps they haven't been emphasized in this workshop. So the first is that you need to find a good initial basis or set of features. And that's before you do regression and enforce sparsity on the regression coefficients. Secondly, in a more complex setting, you also need to find a parameterization and a metric that reflects the intrinsic, possibly nonlinear geometry of the data. So, for example, if you have data along these banana-shaped structures, then you need to find a parameterization that reflects this. So I will present two complementary approaches here. So the first is treelets, which is a method for feature extraction and multi-scale analysis. The other one is diffusion maps, which is a nonlinear technique to learn the geometry and the parameterization of a data set. Now, at the end of the talk, I'll also describe my work in progress on spectral methods. And it turns out that diffusion maps and so-called manifold methods, they do not really perform better than classical non-parametric smoothing in high dimensions. If you look at the convergence rates, they're actually similar. But that's not really the point with spectral methods. And I'll get back to that later. So first, feature extraction. So treelets is an orthonormal basis that combines some of the advantages from both PCA and wavelets. So as in PCA, it's data-driven. It performs an eigenanalysis of the covariance matrix, but the analysis is local. The method also has a faster convergence rate than PCA. And that makes a difference when sample sizes are small compared to the dimension. It's also more robust than PCA in the presence of noise. As wavelets, it's multi-scale, but the method is not dependent on the initial ordering of the covariates. So there are certain applications, for example, genetics, where document arrays, where you can use treelets, and where classical wavelets may not be as appropriate. Okay, so as in wavelets, we form fine to coarse representations of the data, but we build adaptive functions on the data. Okay, so here's the algorithm. So let's see here. We start at the bottom of the tree. We find the two variables that have the highest correlation, and then we perform a 2D PCA. So it's a rotation in a two-dimensional in a plane here. And we coarse-grain the variables with the first principal component, and then we describe the residuals with the orthogonal complement, which we save for later use. Then at the next level, we treat the coarse-grained variable just as a regular variable. And then again, we'll look for the pair with the highest correlation. Then again, we perform this rotation. So we perform this series of rotations all the way up the tree. So as in wavelets, we save the residuals, and that gives us the multi-resolution analysis. So we have a set of nested scaling spaces and also residual spaces for the difference between the scaling spaces. So the final result is an orthonormal basis, and it consists of the coarsest scaling vector at the top of the tree and then the residual vectors from each level of the tree. And that's our basis. So the algorithm returns two things, a hierarchical tree and an orthogonal basis. And both of these reflect the structure of the data. So you have the scaling vector and the difference vectors that show the intrinsic grouping structure on multiple scales. And the coefficients, S and D here, give you an idea of the importance of these vectors. So let's look at a simple example of how treelets can uncover the localized structures of the data. So here the input vector is a random vector with 3 groups of statistically indistinguishable variables. And these groups are also weakly correlated, which makes the problem a little bit harder. So ideally, we would like to compute loading vectors that are indicator functions of these hidden groups. And this is also what treelets are doing. So we compute the treelet basis, we look at the energy distribution, and in this case, we will have 3 vectors with large coefficients in a simple example. And the figure to the right shows you the loading vectors. So in this case, they indicate the functions of the hidden groups. So you can say that the method identifies the relevant variables. PCA, on the other hand, will compute these global loading vectors. And it's hard to infer the underlying structure from these vectors. You can also explain these results analytically by looking at the block covariance model. So here we're assuming k blocks, and you can show that if variables in different blocks are weakly correlated and the noise level is not too large, and you can make this precise, then you will have k treelets with large coefficients, and these vectors are asymptotically piecewise constant on each block, even if you, regardless of the ordering of the original covariates. So how about the statistical properties? Well, that's the neat part, because you can show that treelets has a faster convergence rate than PCA. So as you know, PCA is consistent if the sample size is much larger than the dimension. But for treelets, if you have structure, it only needs to be larger than the log of the dimension. So that's a significant difference. The method is also more robust to noise. So, so at each level, you make a decision whether you should merge a variable with a block or not. And as you go up the tree, you're averaging variables, and that creates entities that are more stable. So you're actually less likely to make a mistake when you go higher up in the tree. So it makes a lot of sense to go find a course in a series of rotations rather than just doing the whole rotation at once. I'm going to skip the details because you can read about that in our paper, and you can also ask me about it later. So I'm instead going to look at data now. So how about more complex situations where you don't really have these exact block structures and where they at best are only approximate? Well, in that case, you don't get these exact indicator functions. But if there is structure, you will get continuous valued indicator functions. So here's an example for hyperspectral data. So again, at each pixel, we have a spectra. And I've labeled 3 different tissue types, and you can see examples of the spectra. So the task here is tissue classification. And I want you to show what the tree lists look like. So here we group together variables that are similar in a hierarchical fashion. And this is the tree structure that is learned. And this figure here shows you the series of rotations we performed at each level of the tree. So this is a special case of the grand tour, but we're not using it for visualization, but we're using it to compute the basis. So here we have the course scale and vector, and the other rows show you the loading vectors at the different levels. So these are the difference vectors. And as you can see, by construction, each basis vector is local and is supported on these nested clusters in the tree. We have this multi-scale analysis when you look at the union of all these vectors. Just as a comparison, I'm showing the loading vectors for PCA. And as you can see, they're global, and they involve all the regional variables. And there's no sense of a multi-resolution analysis. OK, so here we use the training set to construct the basis. Then we sort the tree-leaf vectors according to the discriminant power. So here are some examples where we show the most discriminant, the three most discriminant vectors. And then we'll perform a dimension reduction by projecting our data onto a subset of these vectors. OK, so what are we doing when we do this projection? Well, effectively, since we have these waveforms, we're effectively averaging bands in adjacent that are adjacent because they're correlated. And we're taking differences between two different groups. OK, so now we build a classifier in the lower dimensional space after we projected the data. And this figure here shows you the misclassification rate on a test set. So the blue line here shows you the rate if you had used all the original covariates. The green curve here shows you the results as a function of the number of treelets. So what you see here is that if you use 3 treelets, you do as well. And if you use more, you are doing better, and then eventually will go up. So here we're effectively regularizing the data, but we're doing that in a smarter, adaptive way. So I just want to show you quickly an application to microarray data. So here, each column here shows you the expression profile of 72 patients across 1,000 different genes. And we're going to use treelets here both to explore the organization, the structure in the genes, and the structure in the samples. So first, we apply the treelets to the genes, and then we project the genes onto this lower dimensional representation, onto the treelet features. And then we build treelets on the samples, and we use those treelet functions on the samples as continuous valued indicator functions of the labels. So I forgot to say that the 2 classes, so the patients either have 1 or 2 different leukemia types. And the picture here shows you the dominant or the maximum energy treelets on samples. So the blue dots are the correct classification labels of the samples. And this red curve here shows you the second course's treelet function. And what you see here is that the loadings, they track the correct labels pretty well. And in this case, there's only 1 or 2 samples that are mislabeled, 2 patients that are mislabeled. And that happens at the points where the loadings are small. So the bottom line with this example is just that it's more than just clustering. There's actually information in the basis vectors themselves. And it's also not any type of averaging of the covariates in a cluster. So I'm just going to quickly summarize the first part. So we presented treelets, which is a multi-scale basis that's inspired by hierarchical trees and wavelets, and hence the name. It's fully adaptive, and it's especially well suited for data where you have groupings of variables and cases where sample sizes are small. Now, an interesting question for this workshop is whether treelets can improve regression, especially lasso-type methods that don't perform so well when there's collinearity. So the question then is, what if we change the basis and use treelets first? Does that improve the performance of regression? But I'm going to switch gears now and instead ask, what if you have nonlinear structure? So we're going to start with a data analytic approach. So assume now that you have a given set of objects. So how do we define a distance measure and a coordinate system that makes sense? Now, in high dimensions, usual distances are often only good locally. So here's an example. We have two rotated, or your pictures of two rotated versions of the same digit. So now if you compute the Euclidean distance by subtracting the two images, you're able to detect changes for small rotations. But if the rotation is large, then these two images are they're totally uncorrelated, and the Euclidean distance is essentially meaningless. Okay, so how do we go about this? Well, imagine now that we have several instances of this digit, and that the parameters that control the variability are sufficiently sampled. Well, in that case, we may be able to learn the global structure by integrating overlapping patches of Euclidean geometry. And this is exactly what we do in diffusion maps. So much of this work originates from Stéphane Lafond's PhD thesis. We're also a group of researchers who work on this framework, including Bos Nadler, who gave a talk yesterday, but on a different topic. So the starting point here is that we have a similarity measure that makes sense locally, and then we integrate this local information into global representation by a diffusion process. So we're going to view the data as nodes in a graph, in a weighted graph. And we can define the weights in the graph by, for example, a Gaussian kernel that localizes this information, and epsilon here is the bandwidth. And I'm going to get back to how you should choose your bandwidth. Then we'll construct a Markov chain on the graph by, based on the weights, by defining a row stochastic diffusion kernel. So we normalize the rows in this weight matrix to 1. And we can then think of this kernel, Pxy, as the transition matrix of a fictive Markov random walk on the data. So element xy can be interpreted as the transition probability from x to y in one step. And the direction and also the speed of this random walk depends on the similarity measure. So if 2 points are similar, you will have a higher probability of transition. Okay, so interesting things happen when we take powers of the transition matrix. So you can think of the mth power of the kernel as the probability of transition from x to y for an m-step random walk. And this is interesting if you look at the conditional probability Pmx dot of starting at the point x. You can think of that as a feature vector that measures the interaction between x and all the other nodes in the graph. And when you increase the power m, you're propagating this short time or local influence in the graph. So geometrically, you can think of the conditional probability as this feature vector as a bump that's centered at x with a certain width that depends on m. And the width increases. But it's not the same as just increasing the bandwidth because you're integrating over all possible paths. So when you do this, you're capturing the connectivity of the data or the geometry of the data. And we're going to see some examples of that. Then we define the diffusion distance as the weighted L2 distance between these conditional probabilities. So the diffusion distance between x and z, it reflects the connectivity of the data. It's small when there are many paths connecting the points x and z. So if you take the example here, the Euclidean distance between A and B and C are the same. But if you look at the diffusion distance, B and C are much closer because there are many paths that connect them. While A and B, they're connected by this bottleneck, so diffusion is slow. Now people often ask, when you learn the geometry of data, why don't you just look at the geodesic distance? Well, the geodesic distance or the shortest path is not robust to noise. And here's an example to show what I mean with robustness. So if you take an example with a spiral with noise, we want to measure the distance between A and B along the spiral direction. But if you look at the geodesic distance, you're often taking these shortcuts because of the noise. And you can make this precise by looking at the sampling distribution of the distances. So if you look at the geodesic distance, you have a large variance. But if you look at the diffusion distance, you have a much smaller variance. And that's what I mean with robustness to noise. And the reason is because in diffusion distance, you're integrating all possible paths. So you're less sensitive to noise. I should maybe also mention that it makes a lot of sense to use diffusion distances where when you look at networks, when you look at social networks and you want to measure the distance between two actors. Instead of taking the shortest path, you're taking multiple paths into account and you're integrating all those paths. So you're looking at a friend of a friend of a friend and all those links. Okay, so what's the connection between diffusion distances to a parametrization? All right, so these ideas are very similar to multidimensional scaling. So there's a metric you want to preserve, and you want to find an embedding where these distances are just Euclidean distances. And that's exactly what we're doing here. So you can rewrite the kernel in terms of its eigenvalues and eigenvectors. Then to take powers, to iterate the kernel, you only need to take powers of the eigenvalues. And that's a very fast computation. Then if you rewrite the diffusion distances in terms of the eigenvalues and eigenvectors, you get this expression. And if you look at it, you will see that this is just a Euclidean distance if you use the eigenvectors as coordinates and you weight them with eigenvalues. So this is just like in multidimensional scaling. Okay, so we embed a point x with the eigenvalues and eigenvectors. And then in this diffusion space, we can just compute Euclidean distances, and those will reflect the connectivity or geometry of the data. All right, so now you may wonder, if you've been listening, where the dimension reduction comes from. So if you have a graph with n points, you will have n vectors and n coordinates. Well, the thing to realize is that these eigenvalues will be between 0 and 1. So you have a decay of these coordinates. And when you take powers of them, the decay is even faster. So that means that when you estimate the kernel or the diffusion distances, you don't need to take all terms. And how many terms you need to include depends on the rate of decay of the eigenvalues and also the scale of the analysis. So on the coarsest scale, you need fewer terms. And I'm going to get back to this and make this more precise in the sense of estimation. Well, the bottom line here is that it's the eigenvectors that define the coordinates of the embedding, and the eigenvalues tell you the dimension of the embedding. I'm going to show you some examples. The color is a little bit strange. But, so here we have data on a simple closed curve, and they might be embedded in much higher dimensions. So if you now compute the eigenfunctions of the diffusion operator, you would just get the Fourier basis. And if you embed your data using the Fourier basis, the cosine and sine, you'll get a circle. And here are some results for real data. So here I've extracted small patches from many natural images. And what you see here is the embedding of these patches. And this parameterization captures variability in terms of rotations. So on the border here, you have edge patterns. And if you move along the border, you go from vertical edges, gradually to horizontal edges, and then 180-degree rotation. So we see this in this embedding. And if you move inward, you will see other kinds of structures. Here we have a bar, and then we also have some checkerboard patterns, and they're captured by higher order eigenvectors. So I like this example a lot, because it shows you how you can study the connectivity and geometry of the data by looking at the eigenstructure. So here we have data on a dumbbell. We computed the eigenvalues and then the eigenfunctions. So these are really the eigenmodes. And it's just as in physics, you have these natural oscillations. So the first one is here. So you have this kind of vibration, you have this kind, and then you have the degenerate eigenmodes because of symmetry. So they have the same eigenvalues. So now if you embed the data using these eigenvectors, let's maybe point out this. So you have one eigenvalue that's dominant here, that's non-trivial, and this is the corresponding eigenvector or eigenmode. So the loadings are small on one part of the dumbbell, and it's large on the other part. So if you use that eigenvector as the first direction of the embedding, then the two parts of the dumbbell, they will just go pop, and they will separate. And essentially what you do in spectral clustering or normalized cuts, you're essentially just looking at the first eigenvector. Then you see that you have two clusters. But now if you include all the other eigenvectors, you get a much fuller picture of the geometry and connectivity. And it's also, as I'm going to show, it's also useful for inference, which is our end goal. So here's an example from tissue classification. So at each pixel we have a spectra, and we have a few labeled spectra that I've colored with blue, pink, and green. And here you can see what the spectra look like. So what we want to do is to label all the other spectra in the image. So it's a task of semi-supervised learning. So first what I did was I did a dimension reduction or feature extraction with treelets, and then I used nearest neighbors and Euclidean distances, and I got these results. So they don't look very good. And the reason in this case, this example is a bit harder than the other one, because here you have continuous change of the spectra along the different skin layers, which we didn't have in the pathology slides. However, if I now use treelets and diffusion distances, we're able to learn this gradual change in the spectra, and we're able to perform much better with nearest neighbors. And this is a real example of semi-supervised learning. And it shows how important it is to learn the geometry first before you do other tasks. So it's not just visualization. Yes, Dave?
I'm sorry, how do you see the continuous change in the eigenvalue?
You don't.
Oh, you don't? Ah, okay.
Because it's, you don't see it, but I know that these have different skin layers. And also if you look at the data, you see that. It's more like a little bit like a banana-shaped cloud. Good question. I think Parth also, in his next talk, he's also going to show that these eigenmap methods are not just for visualization. It's important to learn the geometry. So this is just to emphasize that. So learning the geometry improves performance of, for example, clustering. So here, we apply the k-means in the ambient space, and these results don't really make much sense. And in this example, we applied k-means in diffusion space, so we're learning the inherent geometry of the data. And in a paper with Stefan, we also have a rigorous justification for why you would use k-means in spectral clustering. And we actually show that spectral clustering can be seen as an operator compression problem. So this example is to show that eigenmaps go beyond manifold learning. So here we're using eigenmaps to organize and cluster words, and there's no reason to believe that words form a manifold, but we can still learn structure. So in this case, I've described the words in terms of its occurrence in different documents. Then I embedded the data using diffusion maps and applied k-means in the diffusion space. And the results here, the embedding here shows you the organization of the cluster centers. So they're roughly organized according to content. So if you see here, you have cluster centers for, let's say, social sciences, computer science, physics, astronomy, geology, biology, etc. Okay, so there are no manifolds, but it's still doing something. So it's interesting to ask what kind of population quantity we're actually estimating. What are we doing here? This picture is just to show, this slide is just to show the different words that are in a cluster. So in each cluster, we also group together words of similar meaning. So it actually looks like I have a lot of time here. So the last part of the talk is actually the part that I'm most involved in right now. I've been talking about diffusion maps because that's what I've been working on, but there are many links between diffusion maps to other eigenmap and spectrograph methods, in particular Laplacian eigenmaps that Belke and Yogi have been working on, normalized cuts, spectral clustering, and commute time maps. Now, in all these methods, there are many parameters. For example, the bandwidth or the kernel we're using, the Gaussian, for example, the Gaussian kernel we're using. What is the dimension of the embedding? How many eigenvectors should you take? In clustering, how should we choose the number of clusters? And all these parameters, they interact in a very complicated way. And so far, there has been very little research on this topic, very little statistical research on this topic. And from a statistical point of view, it all comes down to asking what are the population quantities we want to estimate, and how do we formulate the right loss function. So in the analysis, in the following analysis, I'm not going to assume that the data lie exactly on a manifold, because of real data, that's never the case. And also we see an evidence that you can use diffusion maps and so-called manifold methods for data sets where there are no manifolds. And I'm also going to look at the unsupervised setting. So we're interested in structure definition and also vector quantization, or maybe, if you want to call it, clustering. So we're going to start by constructing a Markov chain on a continuous state space instead of a discrete graph. So we're going to think of the data as coming from some underlying distribution on, let's call it a data space curly X. And for simplicity, we're going to assume that curly X is a compact set. Then we define the diffusion operator on functions on this set. So we have the diffusion operator A epsilon, where epsilon is the bandwidth. And then we also define the mth power, A epsilon m. Okay, so what are we doing here? Well, these operators, they're averaging operators. And now, if you take m is 1, and if you actually look at this expression, you will see that this is just the classical smoothing operator. The kernel is just the traditional Nadaraya-Watson kernel estimator. But then when you take powers, then you're able to capture higher order connectivity. And that's a concept that's missing in traditional statistics. Similarly, we're going to, based on the empirical distribution f hat, we're going to define the data-based operator A hat epsilon, and also define its power. Okay, just as in traditional smoothing, as the sample size increases, we'll let the bandwidth go to 0. And the question is, what is the limiting diffusion process? And what is the population quantity we want to estimate? So right now, for the finite epsilon case, all the geometry on a certain scale m is captured in the power of these operators. So once you know that, you know the diffusion distances and all other information that we've been computing. Okay. So let's now look at the limiting diffusion process when we go from discrete to continuous time system. So you can think of the time t as the scale of the analysis. And you can think of it as, well, when epsilon is small, as the number of time steps m times a short time transition that's given by the bandwidth epsilon. Now t is fixed because that's the scale of our analysis. But as n increases, you let epsilon go to 0, but you take infinitely many such transitions. And you've probably seen this in classical mechanics or in quantum mechanics, where you generate a finite translation or finite rotation by taking infinitely many infinitesimal transitions. And this is the same idea here. So when you look at the limiting diffusion operator, as epsilon go to 0, that's just an exponential of the generator times the scale of the analysis. Okay, so for a special case that have been analyzed is when you have data exactly on the Riemannian manifold. In that case, the generator is just the Laplace-Beltrami operator, and several researchers, including Belkin-Yogi, Lafon, Hein, and Singer, have shown that. So here we're looking at the general case with a generator. So in the special case, the limiting diffusion operator is just a heat operator. Now we can rewrite this diffusion operator in terms of projectors onto the eigenspaces defined by the eigenfunctions of the generator, and the eigenvalues here are exponential decaying. Okay, so the population quantity we want to estimate is the limiting diffusion operator, and it's a very well-defined problem. This limiting diffusion operator is a bounded operator. Just to show you the difference here, the generator, which in the special case is the Laplace-Beltrami operator on a manifold, is not a bounded operator. It doesn't make a difference when you're doing regression, but when you want to ask questions, what's the dimension of the embedding, or how should you find the number of clusters? How do you do quantization operators? Then the generator will not tell you that, but the heat operator will. Okay, so we want to estimate the limiting diffusion operator, and given data, we construct an estimator by using a finite number of terms in the expansion. We're also using a finite bandwidth, and of course the eigenvalues and the eigenvectors are only approximate because they're computed from the data. Okay, to determine the optimal bandwidth and the number of functions to Q, we need to write down the loss function. And here we've decomposed it in terms of a term we call the bias and the variance. And in the loss function here, we're using the operator L2 norm. And as maybe you can guess, the L2 space is a too-rich class of functions. So we're going to restrict us to smooth functions or functions with uniformly bounded derivatives. So this diagram here is a schematic diagram of the decomposition of the loss into bias term and the variance term. And the bias here is due to using a finite number of components and a finite bandwidth. So these calculations are preliminary, but you can estimate the bias essentially by doing a Taylor expansion and also using a perturbation analysis. And the first two terms are the results we obtained. Then the variance term is computed for finite bandwidth, and it's due to us using the empirical distribution instead of the true distribution. And you can estimate this variance. Well, we estimated the variance by essentially using results from empirical processes. And we obtained this term here. So you might actually recognize this term because, so let me go forward and then back. Because it's computed with a finite width smoothing operator. We're looking at the projectors, difference in the projectors and the eigenvalues. You can rewrite this term. So it comes down to looking at the difference between the averaging operator with finite bandwidth and the true distribution, and the averaging operator with finite bandwidth and empirical distribution. So here we derive the difference. You might have seen this before. And since we also have the eigenvalues and eigenvectors, we get this extra term that depends on the spectral gap. And the Q squared terms comes from using the union bound. So, okay. Well, the bottom line here is that if you minimize, well, we have a well-defined problem, and if you minimize this loss, you can find the optimal bandwidth and the number of components. And you need to use the diffusion framework for that. And the optimal choices of the bandwidth and the number of components will depend on the sample size, also the rate of the decay of the eigenvalues. So I tried to give you some intuition for that before. And also the dimension and the scale of the analysis. So if you look at coarse scale or fine scale, and that's defined by T. Okay, so the take-home message here. Okay, so what's the dimension then? Well, the take-home message here is that spectral kernel methods and classical non-parametric smoothing, they actually have the same convergence rate. Well, you have to formulate what you want to minimize. And the problems are the same. Now, if the data lie exactly on a manifold, then the rate of convergence would depend on the intrinsic dimension of the manifold. And this is the case both for our traditional non-parametric methods and also for spectral methods. However, in the presence of noise, and if you let the bandwidth go to 0, the rate depends on the ambient dimension. Okay, whether you should let the bandwidth go to 0, that's another question. But you should do that in the formulation I have here. Okay, and as I showed you, this is because when we rewrote the terms, what matters here in the variance term is the averaging operator with a finite bandwidth epsilon, and that's the same in Laplace, essentially the same in Laplacian-based methods and in classical non-parametric statistics. It's the operator that's connected to the Nadaraya-Watson kernel estimator. Okay, so then you may wonder, so what's the difference? What's the advantage of doing using spectral methods? Well, the short answer is 2. One is that in spectral methods, smoothing is not really the end goal. You might have the same averaging operator, but you're studying in the geometry and the connectivity of the data by doing the eigenanalysis. So that's the key. You might have the same operator, but you're using the eigenvectors and eigenvalues to learn the structure of the data. And you use that to parameterize your data set. And then you also use the eigenvectors later for clustering, and also, as we see in Yogi's talk, for regression. And if you look in regression and you write down another loss function, then you might see that the advantages in that. The second point is, and this is specific to diffusion maps, I think, is that you take powers of the operator. And when you do that, you take higher order connectivity into account. And you don't really have that in classical smoothing. Because in classical smoothing, when you let epsilon go to 0, all you see at one point is that point. You won't get a sense of the neighborhood. But in our case, if you compute the diffusion distances, even as you let epsilon go to 0, you're still capturing geometry outside that point. And I think there are a lot of applications of this. So instead of density estimation, you may want to estimate, I don't know what to call it, but diffusion densities, points where you have high connectivity. And those would be the hot spots in some data set. So in a network, it might be points where you have a high connectivity, points that are important. And that's not really the same as regular density estimation. So the bottom line here is that spectral methods, they're not really high-dimensional data reduction methods because the convergence rate is not very fast in high dimensions. However, the real strengths lie in data parameterization and the structure definition of the data. So remember that dumbbell example where you sort of unravel the kind of structure you have. So the point is that you learn the geometry by an eigenanalysis. So I'm just going to wrap up here. So I presented 2 complementary methods that both explore low-dimensional structure in data. One is treelets, which constructs adaptive orthogonal functions on a hierarchical tree. The second are diffusion maps, which I would like to call spectral smoothing. And because it's a mix of different ideas. It's a mix of multidimensional scaling, smoothing, and stochastic processes. So the idea is that you learn a global representation and metric by propagating information on local geometry by a diffusion process. So more generally, the bottom line is that if you have complex data, you often need to first find a good initial basis and set of features, and then apply a method that learns nonlinear structure. And as I see it, treeless and diffusion maps are two examples of that. So finally, I'd like to thank my collaborators, Rafi Koifman, Stefan Lafont, David Mumford, Boz Nadler, and Larry Westman. So most of the work I'm currently working on is not published yet, but I hope that, I plan to, in the next few months, post updates on my webpage. So thank you very much for your attention, and I'll be happy to take your questions.
Questions, comments?
First of all, I'd like to say that it's a really nice talk, and I enjoyed listening to it.
Oh, thank you.
When you got you said in your last slide you first look at the linear structure, and that's sort of fairly obvious. But how do you know you have enough linear structure, and you want to go on to the more difficult structure, spectral smoothing technique?
How I know about it? It's a good question. Usually you have a specific task in mind also. So, and you can, the different ways of looking at the data, right? You can visualize the data after I've done the low dimensional projection.
Okay, so you find the linear structure first.
Right. I would, if it's a very high dimensional data set, it's just from my own experience, eigenmap methods don't do very well. If you have 10,000 variables and you just feed it in, and if you have noise, they will not perform very well. So you do need some sort of dimension reduction before that. And also with real data, I would probably start with the simplest approach before I do something more sophisticated. So I hope that answers your question.
Comments? Oh, a quick question. The spectral smoothing approach, your dumbbell visualization and some of your other pictures suggest that this would work well when the structure is actually a mixture of several different kinds of structure.
Okay.
Is that correct, or am I misreading things?
I guess it's a hard question what you mean with several kinds of structure.
Oh, you have a spiral here and you have a cube here.
Right.
And what you'd like to do is understand what's going on with both of these structures.
Right.
But if you try and do it globally, you're going to conflate the signal from both.
Well, if I do it global, I'm certainly going to see that it's two type of clusters because of connectivity. But then if you're interested on structures on multiple scale, that's a problem for all embedding methods. You might want to do it hierarchically, even for nonlinear technique. Is that what you mean?
I think that's
It's hard to use a coordinate system for everything, but I can certainly have a well-formulated problem and say that, okay, all the connectivity is in this diffusion operator. I think of it as a compression problem or an operator estimation problem. How do I best quantize this? And I can do that, but it might not be the things that you are interested in. If it's a more multi-scale structure, you may not want to do that. So. That's a good point.
There's no more questions. Thanks again.